Hi, everyone. Chris Kuzmal here. Last time we were adding zero point 0.1 to a variable called particle count over and over again. And we had started with particle count as 1, and we're adding zero point 0.1 to it per iteration. And then we decided to make it 1, instead of starting at 1, we started at 10,000 because we were suspecting that the error we get due to the difference between the binary floating point representation of a number and the actual number that we want is different. And so we see this point, oh, this 1 here, and then the 2. This is an accumulating an error, and that's okay. But we were thinking it seems to be accelerating, and so we thought, well, let's start where we think we see the acceleration happening. And at 10,000, it wasn't clear. I don't remember. If I went back and looked, maybe I could see that these values over here are starting at a larger. They're larger than before. I don't remember. Well, let's just start at an even larger value rather than starting at 10,000. Let's start at 1,000,000. Okay, and take a look at what happens when we run now. And well, first of all, weirdness, the error is negative. That is to say, rather than adding when we add zero point 0.1, we go down on the third addition of zero point 0.1, we end up with 0.299999. And it actually looks like the error might be smaller. Huh? Is the error smaller? You should look at this. You should run this and calculate it yourself to see what's happening with error. I'm not going to do that right now because I just want to start at an even larger value. Let's start at 1,000,000. 1, 2, 3. Let's start at 1,000,000,000. Woohoo! Now wait a minute. First of all, now our error is positive again. That's weird. And second of all, it's very clear that the number of zeros between this error and the correct value is definitely less than before. And so these errors are bigger. But, well, okay, that is puzzling though. Why is the error bigger? So the error does seem to be accelerating as we are, the error accumulates more rapidly when we are starting from a larger number. Okay, well, we were at 1,000,000,000. Let's go to 1,000,000,000,000. 1, 2, 3. See what happens. Oh my gosh. 1,000,000,000,000, point 1, 1,000,000,000,000, point 2, 0.299. We're undershooting the value, and we're undershooting the value by by 1/1,000th, or is it 1/10,000th? But it's a far larger value than the error that we had before. Okay, 1,000,000,000,000, that's 10 to the ninth, I think. Oh, that's 10 to the 12th, 13th, 14th. Let's try 100,000,000,000,000, see what happens. We're off, and we see now we're off by 1/100th, 1.1, 0.28, 0.38, 0.47. So we're undershooting again, and our error is so large now that it's actually a little bit confusing. It's not immediately obvious that we're adding 0.1 per iteration here. We're adding sometimes 0.9, 0.09 instead of 0.1 per iteration. Our error is 0.01 in adding 0.1. That's a 10% error per addition. This is completely unacceptable, you might say. Okay, well, let's find out what happens if we add yet another zero. I forget what this value is. Is it a quadrillion? Something like that. Okay, we're adding 0.1. Wait, we do a quadrillion, 0.1, quadrillion, 0.2, and then it just skips from 0.2 to 0.4. The error is sometimes it's about as big as the number we're adding. Sometimes it just adds twice as much. Oh my gosh. But you'll notice the width, the number of digits that's been displayed on the screen each time has always been about the same. And that's sort of your clue. Let's add one more zero. And now it looks like it's giving an error. Error, E, 1E, that must mean error. Actually, it's not E error. That means that's an exponentiation. It's 10 to the 16th power. And the value it's saying is always 10 to the 16th power. When we add 0.1 to 10 to the 16th power, we get 10 to the 16th power. Python just gives up and doesn't even bother to add anything once we get to this level. Okay, well, play with that, think about it, and we have to move on though.